Hello, can you hear me? Can you hear me? Okay. Sorry, guys. I actually wanted to do the class on site. I learned from your class rep that they have decided to use the lecture hall. Okay. They have decided to use the lecture hall for an examination. So unfortunately, we had to resort back to our online classes. So I hope you guys are okay with the shift, because I already scheduled a meeting at 2, thinking I will have a class with you in the morning on campus, but unfortunately the exams were held there, so we have to resort here. Anyways, those who have not been able to join, they can watch the recording. Okay, as usual. My camera has an issue. But before we start, I would like to urge all of you to make sure before the end of the day, you send the head of the class rep. Okay, send the class rep your material, your groupings, sorry, your project groupings. Okay, please do so. Then send your groupings, okay, for the project, because I want to send you the assignment or the project, but without the groupings, I don't know how many projects I should create. Okay, so please endeavor to do so. Inform your colleagues to do that also. Okay, so today we are going to look at DC machines. Okay, we're going to look at DC machines. We have completed the transformer part, and DC machines are electromechanical. We're going to look at how they are constructed. We had a session, the first session we had, we have gone through this, I think, before, but today we're going to go into it in more detail. Okay. Somebody has opened their mic. All right, so there are two types of DC machines. We have generators and motors. Yeah, I need to complete some few. I don't know who is it that is forcing this. Okay. Okay, can you hear me now?
Yes, sir.
Okay. So by the end of this chapter, you should be able to understand the principle by which machines convert mechanical energy, okay, into electrical energy. And you should be able to discuss the operating differences between different types of generators, You should also understand the principle of DC generators as it presents a logical behavior. Okay, so starting with the overview, DC machines are divided into two, and as I indicated earlier, we have generators and we have motors. And they are similar to AC machines, just that the AC machines have AC voltages and currents within them, unlike the DC machines that have only DC. DC machines, normally their output is DC, okay? And this, we have what we call the commutator, which you will just see in the next slide. Sorry, when we come to those, you will see the construction. And this we have also discussed it before. But the commutator can also be called, the DC machines are also called commutating machines. But we hardly use them nowadays, actually, because the AC machines are more efficient. You need to have, like, you need to excite a DC machine with a very high current and voltage in order for you to generate the same amount of current and voltage in the case of AC. In terms of construction, also, you need to have a small DC machine, a small AC machine can give you something a big DC machine can only generate. So that's something that I think if you have watched the documentary I shared about Tesla and Edison, you will also get a full sense of why there was that feud between Tesla and Edison and why AC machines have become the order of the day instead of DC machines. Okay, and you are going to learn about AC machines in the next part of the course. Machines 2 is being taught, is always taught, I think it's in level 4, maybe it's in level 4. So you will learn about AC machines, you will learn about synchronous and asynchronous machines there, okay? So for this introductory course, machines 1, you are always expected to cover transformers and DC machines. So a DC generator is a machine that converts energy into mechanical energy into electrical energy, as we've indicated, using the principle of magnetic induction. Okay, and as you can see here, we have our magnets, 2 poles, north and south pole. In between them, you have your coil. Okay, you have, this is a wire. Okay, you have your winding, and this is a winding that is rotated, that rotates between these magnets. As it rotates, there is an EMF that is induced in the wires, and this is a wire which you can now connect it outside, okay, and you get what? You get power, electrical power. So as you can see, this is mechanical. This rotation is mechanical. Rotation is mechanical, but the output is what? Is electrical. And they are everywhere, this DC, especially if you open your electronic components, you will be seeing this kind of motors or generators inside your electronic component. They are very small, okay? Especially these DC motors. If you look at toys, also toys, you know, a car toy or something like that, you will always see this kind of DC motors in them. And a DC motor converts electrical energy into mechanical energy, and the output is what? DC. What you saw inside is actually what we have here. You will see 2 magnets with 2 poles, and then in between them, there is this plate that is rotating with a wire that is wound around it that comes out from this end. We have the construction of DC machines and how they are being constructed. This is a cutaway view of a DC motor. This part here, I think we've discussed it, is the rotor, the part that rotates, whereas this other part here which the rotor is rotating here. This part is called the stator. Okay, the motor house. And as you can see, these are the poles. Okay, these are the poles, they are visible. Okay, these ones here. These are the magnets that we told you. Okay, the magnets. Okay. So if we are constructing a DC machine, we want to make sure we have something like this. Okay, we have an iron core on the top. We have a coil, which is a windings of wires. Okay, you have a commutator interconnection. Okay, then you will have this insulation. So when we come to the exam and I ask you to write the components of a DC machine, okay, please try to list out these key components. Of course, I will not ask you to draw, but I'm thinking maybe if we can have a way to provide an image for each and every one of you so that we will annotate, okay, or make the labeling on the image and submit it as part of the exam, then I think we can do something like that. I'm thinking if that is going to be possible. Do they do that now? They provide you with your question papers and ask you to return the question papers?
No.
They do something like that. They give you the question paper, you answer on the question paper and you return it.
No, sir, but it's possible too.
Only GSP.
Okay. Only GST do that. Okay, I will talk to the head of department. Yeah, I will speak with the head of department. I will speak with the head of department to see if that is a possibility. Okay. So now let's look at machine windings. We have two types of windings. We have amateur, the winding composed of the armature and the field. Okay, these are two things. And then the armature have what we call the wave, lap, and frog leg, sorry. And then the field, we have two types of fields. We have the self-excited and the separately excited. So for the self-excited, we can have series self-excitation of this winding, shunt, and then the compound. Okay, so let's look at the armature first. In the armature, you will have loops of wires. 1 second, guys. Somebody is texting me. 1 second, sorry.
It
So when you have an armature, okay, we will normally have an this loop of wires that we connect, that we wound, and then, sorry guys, somebody is just bugging me. 1 minute. I okay, sorry. Somebody borrowed my car and now it's with the mechanic for some reason. It's just unfortunate. Anyways, okay, so we're talking about armature. When you armature actually is just the rotor, okay? It's just the rotor. Why is my computer lagging? Oh my god. And as you can see on the rotor, we have so many things. Okay, we have the iron core, the coil, we have the commutator, we have the insulation between the segments, and so on. We also have the ball bearing that allows it to rotate. Okay, we also have the commutator, which is this one, this part. So these are all needed for the generator, for the thing to be moved, for the rotor to be rotating. We all need these components. And this, as it rotates, the magnetic force causes electrons to move, which creates energy. So more specifically, the rotor utilizes this mechanical energy from the engine to move around the stator and also to create a magnetic field. As for the windings, where we have what we call the lap wound armatures, okay? If you look at the lap wound, you have a winding that starts from the commutator, goes around, and comes back. Okay, it's like, if you know lap, a race. If you are racing, you have the lap wound armatures. These are the way the wires are wounded. Okay, they are used in machines that are designed for low voltage and high current, and are used in the starter motor of almost all automobiles. So if you have a car or any machine, bike, then the armatures are used, okay, at the starter. As for the case of wave wound armatures, here you can see the winding starts, goes, comes back, goes, comes back, you know, something like that. So it's kind of making a wave, which is something you saw here. It's kind of making a wave. This type of winding is used for high voltage and low current. And the windings are connected in series in this case. Okay, so there are two types of fields, windings. Now we are done with the armature. Now we are into the winding, and there are two types of windings, as we indicated earlier. We have the series and the shunt. When we say shunt, we mean parallel. Okay, we mean parallel. So if you are modeling a machine, a motor, just like we model a transformer, we have an equivalent circuit of the transformer, and we also have some modeling of the transformer. We also have something similar when it comes to the machines, and this is what we normally have. Okay, this is your machine. Okay, this here is a rotor that rotates. Okay, and here, just like in the case of transformer, we have an amount of resistance, okay, and inductance in the system. And this is similar to the operations in the case of transformer. Okay, when you see this, it's exactly like we explained earlier, because you have the winding, you have the copper, you have all that, all these things come into play. So when you have a series winding, because in the case of series windings, the windings are connected in series, and they are made with few windings for a very large wire and have very low resistance. So okay, so when you have series field windings, and this we call them series because in these types of windings, we have series connection with the armature. Okay, and they are made with relatively few winding turns of very large wire and have a very low resistance. The windings come in different shapes. They can be either square in nature, or they can be, as you see here, spherical. Okay, but this sphere is like the cable. Okay, this is like the cable going round and round. Okay, whereas this is the core material. Just like we have a transformer, we have a core, and we make windings around the core. Same thing also with the machines. For the case of the shunt windings, we are talking about having small wires, and these are connected in parallel with the shunt or the armature. They are connected in parallel with the armature. They have high resistance compared to the series, okay, but they do not provide as much voltage as in the case of the series, but they have high resistance because they limit current flow. So when you are having a DC machine, it uses both the series and the shunt fields. Each pole piece will contain both windings. For example, as you saw in that image where we have those magnets, okay? So on the magnets, we are going to have these windings connected to the magnets, so that as the rotor is rotating, current is induced in the winding, and this is tapped out. Okay, so this is, and you can see here we have two sets of windings. We have the series and we have the shunt. The series is one in such a way, let's say it starts here, one single wire, then you wind it here, you come here, you wind it here, you come here, you wind it here, you come here, you wind it here, and you take it out. We also have the parallel. or the shunt field winding. As you can see here, we have like 3 sets or 4 sets that are wound, unlike here where we have only one winding. Here we have multiple windings that are wound around the poles, and this provides the parallel nature or connection to the armature. So when you have a statue with the poles and the windings across the poles, okay, you have the terminal box where all the windings end in. So all our windings, when they come, they enter into the terminal box. And we also have some windings that also reach into our commutator coming out from the terminal box. So as you have seen, we have looked at our windings. We've looked at the armature, and we've seen the number of loops that are generated. Okay, and we've seen the types of excitation. So when you have a DC generator, how it works is you have the conductor that is moving within a magnetic field in such a way that the conductor cuts across the magnetic lines of flux. Okay, and when this happens, voltage is generated in the conductor, and we can tap this voltage to power our devices. However, the amount of voltage that is generated depends on, one, the strength of the magnetic field. So if your magnets have huge strength, then this will have will generate huge amount of voltage. The angle at which the conductor cuts the magnetic field, the speed at which the conductor is moving, and then the length of the conductor within the magnetic field. So these are the 4 factors that determine the amount of voltage that is generated, okay, by a DC generator. So how does this work then? We're talking about principle of operation, okay? All of you are aware, and we have discussed this in the previous, or in our second lecture, I think, or the first lecture. We've looked at the Fleming's right-hand rule. Okay, if you have a wire, 2 magnetic force, it follows the Fleming right-hand rule. Okay. To understand the direction of induced EMF or current of a conductor, we use the Fleming's right-hand rule. So if you look at the Fleming's right-hand rule, if you put your hand out, your right hand, you raise your thumb up, okay, your index finger facing in front of you, then the induced current is going to be your middle finger. So they are at 90 degrees, okay? Meaning that if your thumb is pointing at the force, the motion force, and then the index finger is now pointing at the direction of the magnetic field, then the induced current will be in the direction of your middle finger. So if you look at an elementary generator, for example, let's assume this is your statue. You have the north and the south, okay? And you have the force moving up like this. If this is your magnetic force, because this is where the magnetic force moves, right? Magnetic force moves from the north pole to the south pole. Then the current is going to move also in this direction. It's going to be parallel to them, right? This is going to be the current. Okay. So that means if we connect in the commutator, if we connect a source, a power source, we will end up with this being our terminal that we can connect our load to. Is that clear? If somebody is making noise. Please mute your mic if you are not asking a question, because this is important. That's why I am asking if it is clear. Okay, this is not something you want to read. And understanding this part is very important. If you look at your cable, right? Well, let's start with simple. This is the magnet, this and this. If this is the North Pole and this is the South Pole, by default, you know that magnetic force moves from the north to the south, okay? It moves from the north to the south. So that means if it is moving horizontally, at least we know this direction. Then we can also determine the direction of motion. For example, if this is the direction of motion, okay, the field is going that. Then our force, the force, which means the force that is going to be induced what happened
Apo lao tayo na bon.
Allah una di ma a swear to you.
Such a very.
So lecturer no dey who says this thing na who interact. Lecturer for what now? I don't want my mindset.
Oh, I think they saw.
Normal o. You na your Gmail you go put sef na what for you.
Where class rep dey?
But you dey house ne? That's why you don't attend.
Eh?
You dey house?
I dey house now.
I fit say this thing.
Sancho.
I dey house. Not tired, I no sleep.
I don't on music. On music.
Sharp, sharp. Beg. Sai ka kashe ai. Ya dawo ka kashe sharp. Ka samu da rema.
I keep quiet. Ina wuce lissafi ne, ya gane.
Harry Maguire dey ask where the lecturer dey. Go back to Manchester.
And lecturer ya dawo ya ji waka da wow. This thing is out here. Stop my data. This is just the come out.
Okay, guys, can you hear me?
Yes, sir.
So what
Yes,
happened?
yes, sir.
When did I miss out? I just
Since
We thought you went
for
somewhere.
like how many minutes?
Like,
about 10 minutes.
10 minutes.
yeah.
Yes, about 10 minutes, 6 minutes or 10 minutes ago.
Okay. Did I finish motor DC motor before I disconnected?
No, no, no.
No, sir.
Yes, yes.
Chey. Okay, let me come back. I don't know. I didn't need to realize that I'm oh my god. Okay.
So welcome back.
Thank you. Okay. So, but we finish with the elementary generator, right? Have I treated the practical
We are in that
generator?
area.
Okay, let's quickly just go back a bit. I don't know if it is the network or if it is my system that is slow.
It's Nigeria.
It's Nigeria. Let me reduce the workload of my system. Okay. Okay. So I hope it's still recording, just in case for those who are, yeah, it's still recording. Okay, so as I was saying earlier, we have what we call the elementary generator, okay?
We're not here.
You cannot hear me.
We were not in this place before it disconnected.
The call ended. Okay.
We were not in this place before it disconnected.
Okay. What of the flaming right-hand rule?
Yes,
We
I think that's
passed.
Okay, let's
Yes.
start from here. Okay, so the flaming right-hand rule tries to help us. It is also called the generator rule, okay? It is also called the generator rule, Fleming's right-hand rule. So what Fleming found out was that if you have, if you have a magnet with two poles, north and south, and you have a winding, okay, like this, assuming this is a, just this is a wire, okay? This wire is going to be rotating up and down, because the magnetic force is going from north to south. I'm sure you know of that, right? It's going from north to south. So assuming this north and south is placed on a table, and then you have this north to south. Okay, so let's assume this is it, going like this. Then the cable is going to be rotating up and down. Okay, so up and down, up and down. If that is the case, if this is the magnetic field, which is going north to south, as you can see in this diagram, okay, north to south, going this, and then the motion, which is the cable that is rotating up and down in this field, is up and down, which is by your what? By your pump, okay, by the thumb, whereas this is the index finger, okay? Then the direction of the induced current is going to be given by the middle finger if it is put at a perpendicular to the index finger. So that means our current now is going to be moving in this direction. Okay? So that's why it is called the Fleming's right-hand rule or the generator rule. It is used to determine the direction of the induced EMF or current of a current moving in a magnetic field. Is that clear? So in an elementary generator, we assume we have permanent magnet, okay, it's permanent. And then there is a winding, okay, a wire loop. There is a wire loop, which you saw here. This is the wire loop mounted on the shaft so that it can be rotated in a stationary magnetic field, okay? So once you bring your wire loop between this, it will start continuously to rotate. Then here, we will attach this, our wire loop, to something called the commutator, okay? This wire loop is going to be induced with an EMF or current, and then we can now connect via the brushes. These are the brushes. We can now connect our power source. So this is like what you saw on your generator at home. You know that socket where you can now put your cable and then connect it to your changeover at home. Okay, so this is what is happening there. Is that clear? I should be checking in. Is that clear?
Yes, sir.
Yes, sir.
Okay. So this is what we call the elementary generator, assuming we have this okay, assuming we have this setup. This is the elementary generator. We have one single north and south with a wire loop, a single wire loop, okay? And then you have your commutator and so on. And this is how it is induced in the generator, okay? We have, for example, our wire loop, it starts at position A, 0 degrees. You will see that this is our meter. Look at the direction is in the 0 degrees in the center. Then as it turns, okay, to 90 degrees, now you can see the current is being induced. You will see the deflection in the meter. When it rotates again to 180, now it is directly parallel to how it started. Then we will see that the pointer comes back to the center, so no current is induced. When it rotates again, now the current is going to be reduced, but from the negative side. Okay, you can see the polarity has changed. Now it's in the negative side. And then once it comes back to its original starting position, same position A, now we are back to 0. Okay, so you can see that the generator has generated current that is changing direction, starting from positive, from 0 to positive, then to 0, then to negative, then to 0, and so on. And when you have a generator, we have what we call an armature, as we indicated earlier. An armature comes up, or the rotor, okay? The armature or the rotor has what we call an axle, and then there is a commutator attached to the axle, okay? So this is the axle, and this is the commutator is attached to the axle, okay? This is the front view of the armature. This is the side view, if you look at it from the side, and this is the top view, if you look at it from the top. Okay. So this is how it works. So the commutator is nothing but just a pair of plates that is attached, okay? This pair of plates that is attached to the axle. And these plates provide the two connections for the coil of the electromagnet. Okay, this connection is what we are talking about. So the brushes which are these red things, they work together with the armature because the armature is connected to the brushes, and then we make our tapping directly from the brushes. Okay, and then we can now see that we are receiving current. So it's as simple as that. That's what the elementary generator is all about. You have a permanent magnet, you have a wire loop, and then you have the commutator, which is here, and then you have the brushes. These are the brushes. Okay, and you connect your wire to the brushes. Is that clear?
Yes, sir.
Okay, so you can read it out. What this here is just explanation of this diagram. Okay, it's just the explanation showing you how things are happening. Okay, so imagine now if we add additional tones, not a single tone like what we have previously. Previously, we have only one single loop. Now we can have many more loops. And each one of them is going to be operating based on the same principle the one that we just finished discussing operates on. Okay. So if each loop, for example, assuming if a loop contains 20 tons of wire, the induced voltage will be 20 times greater than that of a single loop. And the reason for this is that each loop is connected in series with the other loops. Since the loops form a series path, the voltage induced in the loops is going to be added. So what we are saying, for example, if the induced voltage per loop is 2 volts and we have 20 loops, then we are going to have 2 times 20, which is 40 volts that is going to be induced cumulatively. Is that clear?
Yes, sir.
Yes, sir.
Okay. So there is also effect of additional coils. Okay. So when we have additional coils in our loop, also the average voltage is going to be higher than there is, and there is going to be less pulsation of the rectified voltage. Pulsation means what? Going like this, right? Pulses. So if you have more loops, you end up having something like this, which is less. So this is more like a DC. If you see it, it's trying to be as flat as possible. And remember, a DC current is kind of something that is, very flat. It's a flat thing. That's a DC. So the more coils you have, the better it happens in terms of taking care of the pulses of the rectified voltage. After we have done the rectification, we end up with less pulses. So this is for elementary generator, but in reality, you do not have permanent magnet. I'm sure some of you might not have even seen a magnet before. So even coming across a permanent magnet is something that is a bit unrealistic to assume that we are going to be creating a generator with a permanent magnet is a bit unrealistic. So what do we do then? How do we come up with the magnetic effect? So what happens is we will have our core, okay? Core material, which it can be an iron, for example. It's not magnetized, okay? Then what do? We introduce an EMF, a voltage, into a winding. So all this magnet is going to be, as we introduce EMF into this winding, then this ion becomes magnetized, okay? It becomes magnetized. So it starts to act as if it is a magnet. So that when you put a rotor in the center, the rotor will feel the effect of magnetism, and it will start to rotate and rotate and rotate and rotate. Okay, is that clear?
Yes, sir.
All right, so now let's quickly look at DC motor. I will rush this, okay, because it almost follows the same operation with the generator. The only difference is that here Unlike in the case of the generator where we are putting brushes, right? We get our brushes and we connect our cables. In the case of the motor, our main objective is to have that mechanical motion of the rotor. So the shaft, okay, which is the part that rotates, is now what we will connect to our loading. So we will connect it to the loading. Okay. So in a DC motor, the start-2 poles are what's supplied by a DC excitation current, just like also in the case of the generator. So the start-2, this and this. Okay, then this will produce a magnetic field. Then based on that, the rotor is supplied by also some DC current through the brushes. So here we also supply a current into the rotor, just like we supplied current into the starter. Unlike in the case of the DC generator, where we are supplying current only maybe to the poles of the starter so that we create a magnetic field. Here we are applying DC into the starter and DC into the rotor. Okay. Then we have magnetic field induced in the starter, and then the rotor current is going to generate a force that is going to now start driving the motor. Okay, so let's assume this is the magnetic field, okay, moving from north to south. And the poles generate a magnetic field that is perpendicular to the current carrying the conductor. Okay, and we also have the current that is moving there. When these things is happening, we have what we call the Lorentz force. When the interaction between the field and the current happens, we have what we call the Lorentz force. And this force is perpendicular to both the magnetic field and the conductor. Okay, with the magnetic field. This force is what will turn the rotor until the coil reaches the neutral point between the poles. And at this point, the magnetic field becomes practically zero together with the force. However, the inertia that drives the motor beyond the neutral zone, where the direction, so if you know, when you are even, let's say you have your motorcycle, you are riding it to school. If you run out of fuel, it will not just stop abruptly. It will continue to run even though the bike is off. You know, it doesn't have any fuel to sustain its flow or its continuous movement. That's what we call the inertia. Okay, so that inertia will continuously drive the motor beyond the neutral zone, where the direction of the magnetic field reverses. However, we want to make sure we are avoiding the reversal so that something that is moving forward, we don't just want it to start moving backward, because when that happens, then we might end up having accidents. You know, just assuming now cars that are driving the bus that takes people to school, just because the fuel runs out, it starts moving in reverse direction. So we have to avoid that. So that's where the commutator that is supplied with the current is going to change the current direction, and this is going to avoid the reversal of the force direction. So this is the DC motor and how it operates and how it's a bit different from the DC generator. The next thing is the DC machine equivalent circuit. We can discuss this tomorrow. I have another engagement now. Unfortunately, I wish we could have had the class in the morning so that we can go through all of these slides and call it a day for the course. But I didn't know that they will have an exam in the room. So, and I already scheduled a meeting at 2. So I had to push this class to after 2. So let me know if you have available time tomorrow. We can meet at the same time if you are free, if you have no exams. We can meet the same time and we can finish the last part. And this is the part that is a bit more interesting, is the one with the calculations, okay? To see how we get the equivalent circuit of a DC machine, just like we did with transformers. Is that clear? So same time tomorrow, 2 to 3, 1 hour is enough and we can finish this. 2 to 3. You have exams, 2 to 3?
No, no.
No.
Okay. Okay, then please endeavor to attend. Those who cannot attend can watch the recording, and try to submit your report, your grouping to the class ref. Make sure you do that, okay? Submit your groupings to the class ref so that I can dish out the assignments, the project before tomorrow, okay? Please do so. You have any question? Otherwise, I will call it a day.
Sir, please don't forget to share the slide with us.
Yeah, I will do so immediately. Any question?
Thank you, sir.
No question.
Okay.
All right then. Thank you guys. Have a good day.
Abdurrahman.